So back in grade 9 and grade 10, you did a lot of work on finding the slopes of lines. And so that was trying to put a number to how the thing changed, right? Rise over run. And then in grade 10, you did a whole bunch of work about parabolas. And then in grade 11, you did a whole bunch of work on other functions, like the exponentials and the rationals and the sines and the cosines. And not once did anybody say anything about slope for those curves. And if you take a look at this parabola I've drawn for you here, you maybe can appreciate why. The slope of the parabola here, I don't know what the number is exactly, but it has an upward slope. And here, it has an upward slope, but if I grab a marker there, it's not as steep as it used to be. And in fact, at the vertex, the slope of that thing is 0. And then after the vertex, the slope goes negative. So the reason you didn't talk about slopes for those other functions is that the slope of those functions is different depending on where you are. And up until that point, or up until this point, you haven't had the algebra skills you need in order to actually determine the slope of one of these curves at any particular place. So we're going to do a really clumsy version of it. And if you want a more elegant version, you should take the calculus course, because that's the entire purpose, well, half the purpose, I guess, of calculus, is to determine the slopes of exotic functions. But we're just going to do some numerical examples here to get ourselves warmed up as a pre-calculus event. So the thing I'm going to start with then to try and get this done is to start with the slope of a secant to this line. So let me jot that up there. Slope of a secant. Now, a secant is a line that just cuts through the function. So I might draw one from here to, let's say, here. So there's my secant. 2, 1, 2, 2. Like so. Okay. So if I'm going to do a slope, I need to have the rise, so how much the function goes up or down, and then I have to divide it by how far it takes to do that. So in this particular function, I have a triangle forming, if you can see that there. Got this little piece here, drops that much, and then it runs that far. Now I could just count those because I happen to pick convenient places. But if I were to try and do this algebraically, the slope, change in y over change in x, I'm going to have to figure out how high this is first off. So to figure out how far up you go on a function, you just need to take the x value and plunk it in for x and do some calculating. So this particular place is when x is 7, and this particular place is when x is 1, 2, 3, 4, 9, 10, 11, 12, 13. 1, 2, 3, yeah, 13. So I'm going to be determining the slope of a secant on f of x between x equals 7 and x equals 13. Okay. So in order to find out this height here, I'm going to have to take the function and I'm going to have to evaluate it at 7. And then I'm going to have to take the function evaluated at 13. And I'm going to have to subtract the two values. So this thing drops, right, is the difference between here and here. Underneath, I'm going to have to take the gap that this thing goes horizontally. So it goes from 7 to 13. Okay, so to do a little work here, the function at 7 would be -1/4 of 7 minus 9 squared plus 11. So 7 minus 9 is -2. -2 squared is 4. And -1/4 of 4 would be -1. -1 plus 11 would be 10. So when I work this out, then the slope f at 7 is 10. Now I still need to evaluate this thing. 7 minus 13 is -4. I'm just going to erase this then. And I need to get the function at 13. So that would be -1/4 13 minus 9 squared plus 11. 13 minus 9 is 4. 4 squared is 16. Quarter of 16 would be 4, so I end up with -4 plus 11, which equals 7. So the value of this function here at 13 is 7 high. Right. So to finish off here then, 10 minus 7 would be 3, or -4. So I end up with a slope for this secant of -0.75. Or you could leave it as this fraction. Slopes are sometimes more useful as fractions. And if we check here, this thing drops 1, 2, 3, and over. Something funny happened there. 1, 2, 3, 1, 2, 3, 4. Hello, friends. 7 minus 13 is 6. So that's -1/2. So if you can actually do algebra correctly, or I suppose in my case it was subtraction correctly, you can see this line is dropping 1/2, dropping 1/2, dropping 1/2. Right? So all we've done there in order to get the slope of a secant between these 2 points is to evaluate the function at the start, evaluate the function at the end, and then subtract the start x from the or the final x from the start x, and you get a slope. Now if you look at this line isn't even close to the slope of the parabola at that point, right? The slope for my parabola should be a little steeper, and this one, it's not even close. Now if I were to draw a secant here between this point and this point, do you see how it's gotten a little better? And if I drew a secant between here and here, that'd be really good too. And if I drew it between here and here, as I draw this second point closer and closer and closer to this value, my secant starts to approximate the slope of my curve at that place. So I need to take this function then, and I'm going to try and get the value of the slope of the parabola when x is 13 by creeping up slowly with the other point. Now if you can think back a few weeks to an operator that allowed you to creep up on a value but not quite hit it, that's what a limit is. So if I were to take this formula then and change it so that it's slope of a tangent. Now that's a line that just grazes the curve and has the same slope as the curve at its particular point. We're going to do the slope of a tangent on this function. Instead of between two values, I'm going to say at x equals 13. So I need to change this function a little bit. I'm going to move this so I have a little bit more space. First off, I'm going to keep the 13, and I'm going to make this into some other letter. So I'm going to choose a P just for fun. And what I'm going to do is take this value of P and I'm going to try it at 10, and then at 12, and then at 12 and a half, and then at 12.75, and then at 12.9, and then 12.999, and then 12.99999, and I'm going to keep doing that until I can see a pattern in my limit that's going to tell me what the slope of my parabola is at that particular place. So what I'm doing is I'm taking the limit as this dummy variable here gets closer and closer to 13. Now, if you look at the bottom here, you can see why I can't just put 13 here. 13 minus 13 would be 0, and I'd end up with a division by 0, which is forbidden. So I have to creep up on this value and get as close to 13 as I can without actually hitting it. If I do this, so instead of just plunking in some random other place, if I let it slide in close, I've changed from slope of a secant to slope of a tangent. And so I'm going to use different symbols for that. Instead of delta y over delta x, I'm going to use a d. Delta is the Greek letter for d anyway. And my function wasn't named y, my function was named f. So this is the change in f over the change in x. That's the slope of my tangent right there when x is 13. I'm going to erase this down here. So first thing I'm going to do is evaluate f at 13. And I think if you rewind the video, you'll find that f of 13 happened to be 7. So my function here then, slope of my tangent at that point is the limit as p goes to 13 of minus 1/4 p minus 9 squared plus 11 minus 7 over p minus 13. Now I can simplify this up a little bit. 11 minus 7 is 4. So I end up with df by dx is the limit as p goes to 13 of minus 1/4 p minus 9 squared plus 4 over p minus 13. Okay, so I'm going to need a calculator for the next spot, so give me a second to grab one. Alright, so when you're doing limits and you're doing them manually, you just have to pick a number that's close to 13 and then plunk it in the equation and see what you get. So I'm going to try p is 13.1. That's really close to 13. So if I try that, let's see, 13.1 minus 9 is 4.1. Square it, I get 16.81. Divided by 4, I get 4.2025 negative. And if I add 4, I get negative 0.2025 divided by down here, I have 13.1 minus 13, which is 0.1. So this is worth negative 2.025. So that's okay. So I'm going to try another one, getting a little closer. I'm going to try P is 13.01. So I'm going to take this number, put it in for P here and P here, and see what I get. So 13.01 minus 9 is 4.01. Squared is 16.0801. Divided by 4, or sorry, times negative quarter, whichever you want to do. It's negative 4.020025 plus 4 gives me negative 0.20025. That's what the numerator turns into. The denominator would be 13.01 minus 13, which is 0.01. Oh, sorry, there's an extra 0 in here. So let's just rewrite the whole top there, dummy. 0.020025. So this divided by that ends up giving me minus 2.0025. Well, you notice that this digit has stayed the same, and this part of it has just moved down the line. So let's try and get really, really close. Let's try P is 13.00001. So the numerator then would be 4 zeros and a 1 minus 9, which is 4.00001. Square it is the 16 and a whole bunch of other stuff, times negative a quarter gives me negative 4.002 plus 4 gives me negative 0.0001. I'm not real happy about that. Let me try that one again. 13.12341 minus 9 squared times 0.25 negative. Okay. Plus 4. Negative 0.00002. And the denominator will be 13, and this mess minus 13, leaving 0.00001. And if I divide those, I get, oh, my calculator was not showing me all the digits. I get minus 2.0000025. Again, I have this here. This negative 2 has stayed, and the rest of the garbage is just moving on down the line. So if I look at these things, I would say, based on limits, that as p approaches 13, the slope of this parabola is approaching negative 2. Let me just put that in the box for you. So I took this thing, which was the slope of a secant, and I put in this limit so that I could make those secants ever and ever closer to each other, so that the start and the end point basically on top of one another. And if I did that, I ended up taking a limit and getting a value of negative 2. So if I'm going to go to this place right there, I'm going to travel from there along a line with a slope of negative 2. So from here, if I drop 2 over 1, drop 2 over 1, drop 2 over 1, and following the path the other way. Look at this line. The parabola approaches this line, curving into it. They're basically parallel at that spot, and then it curves away again. So in here, if I erased everything else about that parabola, you can't see the line I drew and the parabola as different because they are parallel and on top of each other at that particular point. So this limit thing has allowed me to approximate the slope of a parabola by using the slope of a tangent to that parabola at a particular spot. Alright, so I'm going to try and determine the slope of a tangent to this particular curve, this exponential, which I've drawn for you, when x is 3. So the x value of 3 is 1, 2, it's right here. So I'm going to find the slope of this particular function at that place. Alright, so in order to do that, the slope of a tangent, so d, this function is named g, so dg of dx is the limit as my dummy variable approaches this value of the function at the dummy variable minus the function at the place in question divided by the dummy variable minus the place in question. And so this is just rise, right? How much does the function go up and down between these two places? And this is just run. How far is it between the two spots? So first thing I'm going to do is actually use this equation and figure out what g at 3 is. So g at 3 would be 3 times 2 to the exponent 3 minus 4 plus 3. G at 3 would be 3 times, that's 2 to the minus 1 plus 3. That's 3 times 1/2 plus 3. Half of 3 is 1.5. 1.5 plus 3 would be 4.5. So I'm going to replace this little structure in my equation with 4.5. So the slope of this tangent is the limit as the dummy variable approaches 3 of the function evaluated at the dummy variable. So I'm just going to take this and I'm going to put the dummy variable in. So 3, the 2, the p minus 4, plus 3, minus the value of g at 3 is 4.5, over p minus 3. Now 3 minus 4.5 is negative 1.5, so I can write it that way. So the limit as the dummy variable approaches the value I'm after, 3, 2 to the p minus 4 minus 1.5 over p minus 3. So the only thing left to do then is to evaluate that limit manually. So I'm going to have to try and pick some numbers that are close to 3. So let's try 3.1, 3.001, and 3.00001. Jot that in there. Try p equals 13.1. Alright, so if I do that, the numerator here would be 13.1. Why am I doing 13.1? I want 3.1. I think I have the last question stuck in my brain. 3.1. If I put that 3.1 here, I'd have to do 3.1 minus 4 is negative 0.9. Then I would have to do 2 to the exponent negative 0.9, which gives me 0.535886 times 3. I don't like what's happening here. Let me try this again. 3.1 minus 4 is negative 0.9. Clear. 2 to the exponent, negative 0.9 equals 0.535887. Multiplied by 3 is 1.60766 minus 1.5 is 0.10766. Now in the denominator here, 3.1 minus 3 would be 0.1, which puts this at 1.0766. So that's my first guess. Now I'm going to try P is 3.001. So if I put that into the calculator, up here, 3.001 minus 4 is negative 0.999. 2 to the exponent, 999 negative, is 0.50034666937. Multiply that by 3, gives me 1.501 minus 1.5 gives me 0.00104000812. And if I put 3.001 here, subtract 3, I get 0.001. Divided by 0.001 is 1.04008. Okay. Get a little closer. Don't be shy. I think that's a commercial for deodorant from the 90s. You can see how rotten my brain is. If I take 3.00001, put it in there, 3.00001 minus 4 gives me negative 0.99999. That's 5 nines. 2 to the exponent, 1, 2, 3, 4, 5 nines, but negative, is 0.50000346657. Multiply that by 3. Subtract 1.5 gives me 0.000010397. This number here in the denominator would give me 0.00001. Gives me 1.0397. All right. So what's happening to these numbers as I get closer and closer and closer to 3? Well, these look like they're settling somewhere around 1.03 and a bit. So it looks like the limit, as P goes to 3, dg by dx is going to 1.039-ish. Now I could keep going to be more precise, but I think that will do. So if I were to go to this particular spot and I were to travel along a line with that slope, 1.039, then from here I'd have to go up 1 over 1 and a bit, over 1, up 1 and a bit, over 1, up 1 and a bit, over 1, up 1 and a bit, and same pattern, down 1 and over, down 1 and over, down 1 and over, down 1 and over. And I end up with this tangent line that comes in, clips the function, and carries on. It's really satisfying when it works out that way. So you can see that I've got a tangent forming here, because if I were to cover the function, everywhere but right at that line, you can see that they are parallel at that particular point. So I've figured out then, after all of this work, that the slope of this particular exponential when x is 3 is somewhere around 1.039. I'm just going to write that down up here. dg by dx is approximately 1.039. Okay. The last thing that we're going to do with this is to actually determine the equation of that tangent line. So get the equation for the tangent. So equations of lines need two things. They need a slope and they need a y-intercept. And so far, I have the slope working out for me. So I need to calculate the y-intercept of this line. And it looks like, just on the graph, that it's somewhere around 1.5-ish. So how am I going to do that exactly? To get the equation of a tangent, you have to remember that a line has two particular values. It has a slope and a y-intercept. And I can look at this line and see that there's a y-intercept here somewhere around 1. So I'm going to try and calculate that more specifically, more exactly. So I have to remember that the equation of a line is this, y equals mx plus b, where that thing is the slope. So I'm going to take my 1.039 and I'm going to be able to drop that in right here. If I had an x and a y pair to plug into this, I'd be able to calculate the b. And if you recall earlier in the video that I had calculated an x value of 3, so I could put that here. And we also calculated that this function at 3 had a value of 4.5. So I can put that 4.5 here, and then I have everything except for the y-intercept. So if I drop those numbers in, 4.5 is my approximated slope, the x value in question, plus b, 1.039 times 3 gives me 3.12. I'm going to kick this to the other side. 4.5 minus 3.12 gives me 1.38, which is about where I've got it showing up on the grid here, right? That it's a little bit more than 1. So therefore, the equation for my tangent of the line tangent to g of x at x equals 3 is y equals my slope, 1.039, x, plus my y-intercept, 1.38. So the neat part about all this is if you've done all this work, you can go grab graphing software, something like Desmos, and you can type this function in and get it to render it for you. And then you can type in the equation of your tangent and you can see if they actually clip each other at that place. So that not only can give you some insight as to how to stretch and transform and translate these functions, but also to see what their slopes are and if you're doing your tangent questions correctly.